Just how well your Skyhawk performs under different atmospheric conditions is the kind of information anybody smarter than a zucchini would like to have. Obviously, such knowledge will allow you to take full advantage of your bird's capabilities and should result in safer flight. So let's talk about some of the factors that determine performance. Aircraft performance depends upon the number of air molecules available. It's as simple as that. Let's see why. First, the engine derives its power from air molecules reacting with fuel molecules to produce energy. The more molecules available to combine with the fuel molecules, the more energy. Second, the wing produces lift in proportion to the number of air molecules flowing over it. More molecules, more lift. And finally, the propeller produces thrust by grabbing gross handfuls of air molecules and hurling them rearward so that Mr. Newton's third law can do its thing. More molecules, more thrust. Now, we can't actually count the air molecules, of course, but we can make comparative observations. More than, less than, the same as. That last one, the same as, is the key to everything that follows. The number of air molecules in a given volume of air varies with pressure. Higher pressure, more molecules. And the number of molecules varies with temperature, too. But in this case, higher temperature means fewer molecules because they are farther apart. Using these two facts and something called the equation of state, most freshman physics majors can calculate the density of air under various combinations of temperature and pressure. Density, of course, is a nice technical-sounding word for number of air molecules. High density, lots of molecules. Low density, fewer molecules. Fortunately for us, we never have to actually compute density. The physics boffins did that for us a long time ago. They also express the results in charts and tables as density altitude, to keep it in pilot language. Beware, though, when someone says high density altitude. The high is referring to the altitude part, not the density. So think high altitude is thin air and therefore fewer molecules. Conversely, low density altitude means close to the Earth, thick air and more air molecules. To find density altitude from charts or tables, all you need to know is pressure and temperature. All the stuff you need to get that is right here in the cockpit. Pressure you can read from your altimeter. Remember all that pressure altitude business? Well, here's where it goes to work. Enter 29.92 in the altimeter window and read the hands. The altimeter is a pressure gauge, right? Setting it to 29.92 is like making the zero adjustment on your bathroom scale. It tells you the pressure compared to standard at sea level. But don't cheat and do like I do and set it back 5 pounds. It won't work. Temperature is even easier. Just read it off your dual-time stopwatch voltmeter thermometer over here. You have to wonder about an instrument like this, don't you? Did someone in legal say, look around and see if there's anything we forgot to tell him? Can you imagine what that name would look like in German? Anyway, push the top button until you get a reading in Fahrenheit or Celsius. Your choice will depend on the values used in whatever chart you're going to be working on. So now you have the information you need to get a head count on those pesky air molecules using this handy density altitude chart here. Let's suppose you're sitting at Boulder, Colorado, which is at an elevation of 5,288 feet. When you crank 29.92 into the altimeter window, the hands show 5,750 feet, which is your pressure altitude. And the Davtron gives 59 degrees Fahrenheit. So here's what you do. You first find the pressure altitude on these slanting lines here. 5,750 is 3/4 of the way up from 5,000 to 6,000. So make a line parallel to 6,000 right about there. Now, come up from the temperature line from the bottom, staying just a degree left of 60 degrees until it intersects with 5,750 pressure altitude right there. Now, follow horizontally over here to the left and read the density altitude of just about 7,000 feet. Did I hear you say that's nice, but so what? Well, what this means is that even though the airplane is sitting at an elevation of 5,288 feet, because the pressure is lower than standard and the temperature is warmer than standard, the airplane will perform as if it were at 7,000 feet. It means the number of air molecules available to make your Skyhawk's engine purr, its wings generate lift, and its propeller produce thrust are the same as at 7,000 feet on a standard day. Can you see the sheer beauty of this? The engineers have written up performance data for selected density altitudes. Now, all you have to do is measure pressure and temperature where you are, then look in the performance manual under the density altitude that has the same number of air molecules. Elegant. One manual can cover all the different combinations of temperature and pressure that you may encounter in the real world. What you encounter in your own imaginary world is something entirely different. One well-respected aviation trainer suggests that you call density altitude performance altitude. It's an unofficial name, but it pins down just what that altitude number means to you. Notice that on the chart, if you raise the ambient temperature, ambient just means the air around you, and keep the pressure altitude the same, the density altitude will be raised. And this line right here is the standard temperature line. It marks the temperature where pressure altitude and density altitude are equal. And by the way, this standard is international, so sometimes you'll see ISA for International Standard Atmosphere attached to the chart somewhere. And now you have an understanding of one of the key elements in predicting performance. In a later lesson, you'll find out some other ways to collect the information you need to compute density altitude. You'll also be introduced to some other factors that you must consider because of their effect on your Skyhawk's performance. But best of all, we all now possess the information that proves we truly are smarter than zucchinis.